which means 1 degree from 1860. 1 degree is something that cannot be perceived by humans. So we cannot perceive a difference in 1 degree. If during summer you have 41 degrees instead of 40, it's something that you cannot perceive. But keep in mind that this is an average. So in some cases, maybe more than 1 degree, maybe 3, 4 degrees is something that you start perceiving. But even if we cannot perceive it, it's very important, because 1 degree means at the global level a huge amount of energy more, and this explains the recession of glaciers that we experienced in the last already 150 years. So on the one hand, we have to be very cautious when we listen from people that it's very hot because of climate change. And it's very difficult that a single person or a group of people can perceive the effect of climate change. I wouldn't say that it's a real risk that elder people may die for increased temperature, because an increase of 1 degree is not something we cannot protect from. There are several ways, even without air conditioning, to adapt to, even for elder people, to an increase of 1 degree. So we have to be very cautious about that. But on the other hand, we cannot deny the fact that there is a warming occurring, because if we look at the glaciers, it's clear that there is a warming that is occurring. And if you look at the glaciers from the perspective of a water resources manager, you can understand that there has been a big change, and where people rely on snow melt or ice melting for getting water resources, you can understand that this may be a huge impact. Okay, let me show a graph. First of all, there are plenty of figures in the web on glacier retreat. This is one interesting picture which refers to a location in the Arctic. Okay, the last one is, as usual, the screen is cut a little bit, but there are plenty of these pictures. So there has been a retreat of glaciers that has been very significant. Starting from when? Okay, it seems that it started about around 1750. So before then the advent of the Industrial Revolution. The Industrial Revolution marks a shift for humanity, because with the Industrial Revolution we started increasing a lot our CO2 emissions. The Industrial Revolution is located, some people say that it already started in around the beginning of 1800. Some other people locate it at 1870. I would say that the major revolution was indeed at the end of 1800. Glacier retreat started before than that, a little bit before than that, because for sure we have, we have witnesses that prove that glacier retreat started already in 1750. Okay, if we look to a more meaningful graph of global temperature, there are several of these graphs on the web, and the red is a moving average, is a smoothing. Do you know what moving average means? Yes, I think so. But anyway, it's a smoothing of the yearly observations. And you see that there is a lot of variability from year to year, but you see that indeed there is, this is about 1880. I'm sorry because it's cut here, but it's, you see that there is an increase of about 1 degree. And one important thing to say here, so you see 1880, no, just let me scroll it up. 1880, one important thing to say here is that there is uncertainty in these measurements, because the number of gauging stations, of temperature gauging station increased a lot in time. there is the heat island effect that may affect these measurements. Heat island refers to the heating that we experience in cities due to the fact that urbanization increases the temperature of cities. There is also uncertainty because we say that it's global temperature, but actually it's an average over land. We don't have oceans, as you know, covers 70% of the Earth's surface, and we don't have much measurements into the oceans. So some people say that probably the increase may be lower than that, but there has been an increase, because if we look at glaciers again, we see that there has been an increase. So I wouldn't say that there is a controversy on the fact that we are in a period of warming, because I don't think that this is really the matter of the controversy. And this is for temperature. And let me scroll down, because this is something that I already discussed. Now, as I said, there is a controversy on the origin of global warming, and also there is some scientific controversy related to the progress of change of other meteorological variables, like rainfall. What happened to rainfall? Rainfall is more complicated than temperature. Temperature, it's relatively easy to study because it's a slowly variable quantity. If you measure temperature, it's very difficult that you have sudden changes from one day to another. For rainfall, instead, it's intermittent, and it's highly variable in space and time. Also, temperature is not highly variable in space. And if you refer to the other variables, they are much affected by much more variability. It becomes not easy to study them, and it becomes not easy to measure them, because to measure rainfall, we said that it's very easy because I put a tank outside, and every day I measure how much water is collected into the tank, the depth of water that is collected into it. But, because it's easy because I'm referring to a daily time scale, but if I want to measure the rainfall with a time step of 1 minute, this becomes very difficult. Temperature is not difficult because it's slowly varying in time. Rainfall, even at the scale of 1 minute, is highly variable, and it's difficult to measure. Temperature is much easier. River flows, we know that they are not easy to measure. We don't have many gauging stations. And again, at short time frame, it's difficult. River flows are easier with respect to rainfall because they are more slowly varying. But on the other hand, the spatial scale is usually larger than rainfall because it's not easy to measure river flows. Wind, same thing, high variability, not many gauging stations. So it becomes much more difficult to understand whether something is changed. So this highlights that there are two ways for studying climate change, like for studying water resources. Two ways, deductive or inductive approaches. Deductive approaches means that I use knowledge. I build a model, and then through the model, I try to understand how rainfall, to give an example, changes. So I build a model of the climate system. I try to see what happens to temperature if I increase CO2. And after assessing that the model reproduces temperature well, then I go down to the detail of rainfall, wind speed, with the model. On the other hand, I can use the inductive approach. Inductive means that I study data, what I have. For rainfall, river flow, wind speed, it is more attractive, the deductive approach, because we don't have many measurements. So there are two schools of thought On the one hand, the modelers, they rely on climate models. On the other hand, there are the statisticians that look at information from data. I call them statisticians, but it's much larger, the context. Let's say inductionists, people that try to understand from data. Traditionally, the engineers try to rely on data. The physics, people working in physics tend to trust more models. And this is one of the reasons of the debate. Modelers say that observations are affected by uncertainty. Inductionists say that models are affected by a much larger uncertainty. Therefore, when you look for predictions of future climate, you have to be aware, and the first thing that you have to look at is how the prediction has been obtained. One thing is models, another thing is from data. This review that I'm presenting here is made by an engineer. It's based on essentially on data analysis, but there is also mention to models. Very often the media tend to neglect uncertainty of models in whatever field, not only in climate change. Even when we talk about engineering design, you know, uncertainty is an inconvenient truth. So some people are concerned by revealing to the public that there is uncertainty in the design of a dam, because this means that we cannot predict the risk for sure, which is true. Like when you design an airplane, when you take an aircraft, you know that it has been designed with some small, limited, but still there is uncertainty. There is a risk that we accept because we know that everything that we do is affected by risk. So there are some risks that we are used to manage, like driving a car, which is riskier than taking a plane, of course. So there are some risks that we are used to manage. There are other risks that are a bit more concerning because they are imposed, like building a dam. If I am not a stakeholder, a directly interested person, I don't like that people build a dam over my house because, for obvious reasons, because if I decide to drive a car, it's a decision that I take, it's not imposed. If I am given a risk that is imposed, then it's more. And therefore, when we talk about engineering design, sometimes we refer to structures that, you know, we are concerned to let the public know about uncertainty. And this is another reason of philosophical debate. Should be the scientist clear about uncertainty or not? There is an ongoing discussion on that. I am convinced that yes, scientists should give the truth. This is my personal opinion. But of course, it's a philosophical question. And therefore, going back to my reasoning, we are often told that climate models predict the future climate for sure. And this is something that, of course, as engineers, we understand that cannot be true. There is uncertainty. Uncertainty is rarely quantified. And as engineers, as I said, we have this task of trying to understand what's going on there. And first thing we have to start from understanding the natural variability of climate, because climate has never been steady and changing, always changed. So we have to start from understanding natural variability. Keep in mind that this is a term that is originating controversy in itself, because if we accept natural variability, then it opens a can of worms, like, is human-induced climate change important with respect to natural variability or not? But we have to be aware of that, and the first thing, let's start from climate has never been steady. We had glaciations, and the reason for these glaciations is still not known. And this gives to me the opportunity for saying one important thing. There are a lot of things that we don't know about the Earth system. This is an inconvenient truth. We don't know everything. Today, the model of the Western world tend to accept, tend to neglect uncertainty. We tend to accept only what is proposed with no uncertainty. In the Western world, uncertainty is something that is very disturbing in the modern society. So we are reluctant to accept this inconvenient truth that there are a lot of things that we don't know. In the Eastern world, it's different. They have a different approach to life and uncertainty. They tend to accept uncertainty as a nice feature, because indeed it is. If you think about a personal life that is perfectly determined with no uncertainty, is something that is not exciting, is not stimulating, because uncertainty is also an opportunity. It's important to be aware of that in the Western world, if you talk about uncertainty, people are disturbed about it. But there is much that we still don't know. And this is the reason why climate models are not perfect, because there are some things that they cannot reproduce because we don't know their physical mechanism. Ice ages, why is that? There are several theories, which may be a collision with some bodies, meteorites, can be a change in solar activity. There are several other reasons. I don't go into the details, but we have them. And one important thing to know is that currently we are in a cold period. Currently, if we go back to millions of years ago, 500, this is what we know about glacial periods, and basing on our surveys of ice carots, other kind of information that we can retrieve also from space. And now we are in a cold period. We had periods with temperature that was much higher than today, millions of years ago. Correspondingly, CO2 concentration was much higher, because this is another thing that is often not mentioned. CO2 concentration and temperature of the atmosphere are strictly related, because if for some reason temperature in the atmosphere increases, then the temperature of the ocean increases, and the oceans release a lot of CO2. The amount of CO2 that is released for a natural mechanism by the oceans is related to temperature, is potentially much higher than the CO2 emission by humans, and they are related. This is concerning on the one hand, because it means that if we humans increase the temperature, increase the CO2 emissions, then temperature increases, and then there is a feedback mechanism. The oceans release again more CO2, and then there is a feedback effect that indeed can cause uncontrolled changes. On the other hand, we have to be fully aware of the fact that if for some reason solar activity, temperature increases, then it's perfectly normal that CO2 increases. And even if we reduce human CO2 emissions, there is no way to contrast this mechanism, because we cannot control the CO2 that is released by the oceans. And therefore we know that CO2 concentration in the past was much higher than today, because temperature was higher. And this is something that is recognized by science, well known. And of course we have to go back to several millions of years ago. And therefore this is why people sometimes say, in the past 5 million of years, we never had this high CO2 concentration, which seems a huge number. But if you look at the time scale of ice ages, 5 million of years, it's here. This is 50. So this is why people say, they refer very often only to the past 5 million, not because we don't know into the past, but because in the past 5 million we still are in a cold period at the large scale, And within this cold period, now temperature is increasing. So are we going towards a new hot period for natural causes or not? This is impossible to say because we don't know the explanation for this. There are several links on this webpage if you want to better inspect the theory for explaining ice ages, etc. And keep in mind that here you don't see small time fluctuations. I'm sorry, short time scale fluctuations. Let me see if I have another figure. Yeah, this is a figure that, let me see if I can. No, there is no time scale. But anyway, here it's 2000, and and it starts from 0. This is 0. This is year 2000, and this is the medieval warm period. Here we are about 1400. So we know that these are different reconstructions. Different colors means different reconstructions. We know that around 1500, at least in Europe, because we don't have witnesses from United States, we know from Heiss, Carrots, and from witnesses that around 1500 the temperature in Europe was warmer than today. In fact, glaciers were less extended, so we have remains, oral tradition of people passing the Alps without touching any snow. And today it's impossible. Even after the glacier retreat, it's impossible today to pass only in some part of the Alps. But we know that people, for instance, walked from, in Italy, from Val Tournanche to Zermatt and passed the Teodulo Pass without touching any snow in 1500. We know that the woods were extended up to higher altitudes than today. And we have several other witnesses that were left by monks that observed a much warmer climate, not much, a warmer climate. And in terms of temperature, you see that the difference was according to these reconstructions, it was at the level of the temperature that we had in 2004, more or less. And now, it seems that the temperature that we have today in 2014, you know that in the past 3-4 years there has been another increase of temperature. And it seems that it's higher than in the medieval warm period, but there is a lot of uncertainty in these measurements, while here, of course, there is not uncertainty because it's direct measurements. And the black line is direct measurements. And so, even at short time scales, we have changes of temperature. So this is natural variability. And we can make several other examples. And I think I already showed you this picture, which relates to the Po River flows. And even if you look at the flows of the Po River, you see changes. I'm not commenting this picture because I think we already spoke about it. We saw that there was drought period in the past. For instance, between 1940 and 1950, there was a severe drought which lasted about 10 years. What we know is that there are cycles. There are cycles in temperature, there are cycles in rainfall. We also have in Italy some rainfall observations that started in 1725 in Padua. And if you look at this daily series, you see that there are cycles. And the duration of the cycles can be, some cycles last for about 10 years, other cycles last for 50 years. There is a superimposition of cycles whose motivation is unknown. We don't know why. And also for river flows, this drought that we experienced in the Po River, which means northern Italy, from 1940 to 1950, it's not explained. And nobody still made a research on rainfall during that period to see if it was a rainfall problem or another kind of problem. So there is some natural variability that is to be taken into account. And then there is human influence. Human influence, again, we have to be aware that it's real. We cannot neglect human influence. And it affects climate at several like natural variability, time scales, and spatial scales. The heat island effect is a clear example of human influence. The heat island effect, it seems that people are not concerned by it, not much concerned. Actually, for the health of people, it's more important than global warming, because it means increases of temperature of 3-4 degrees in big cities, and people live in the cities. So it's something that is indeed extremely important for the health of people. There has been a recent study that proved that all the major cities of the world experienced in the past 30 years increases in temperature that are very significant. As I said, 3-4 degrees. It's something that can be indeed perceived also by the human body. And it's due to the fact that, of course, urbanization causes, and the reduction of vegetation, whatever, causes an increase of temperature. The greenhouse effect is not much concerned because people tend to see it as a local problem. There are, of course, changes that apply to larger time scales, so we have global warming. But let's talk about, given that we are interested in water resources, let's talk about rainfall. Climate models produced an increased evaporation after global warming. And the reason is very simple, because you increase the temperature, you increase evaporation. Evaporation means that potentially you have more humidity in the atmosphere. And the increase that is predicted by the Clausius-Clapeyron equation, which is a very well-known physical equation that determines the degree of saturation of the atmosphere, degree of saturation by moisture. The Clausius-Clapeyron equation predicts an increase of about 7% of moisture in the atmosphere per grade centigrade of warming. So there is, for each increase of 1 degree, there is 7% more water in the atmosphere. And therefore, one may say that even precipitation is increased. Now, what happens is that this is what climate models predict. Actually, what has been measured through observations is that global evaporation for some reason declined. This is called the evapotranspiration paradox. The reason is probably the fact that wind speed had decreased for some reason, because evaporation is much influenced by temperature and wind speed. This is probably the reason why global evaporation seems to have been declined. This is based on measurement, which are sparse, of course. Actually, if we look at global rainfall, it seems that global rainfall is stable, and this would be in line with the fact that evapotranspiration is more or less stable. So, this is not reproduced by climate models. This kind of feedback is not reproduced. Keep in mind that the Earth system is for sure robust, otherwise it wouldn't be in the present situation today. It wouldn't survive to millions of years of evolution. So for sure the configuration that is today gained by the Earth system is stable, robust, which means that if there is an increase of temperature, there must be a compensation that avoids reaching a tipping point. A tipping point means that if you pass the threshold, there might be a sudden death of the system. If in the medieval warm period we had the same temperature than today and the Earth system survived, if in the past probably there have been temperatures that were much higher and the system survived, it means that the system has evolved in a way to develop feedbacks that compensate for these changes. So it's not a surprise that if there is a warming, for some reason there is a feedback effect that reduces evaporation, because otherwise, if we accelerate the water cycle, the system may become unstable. Given that the system is stable, it's no surprise that there are compensations, feedback effects. So the moral of the story is that if we look at average rainfall, it's not much changed. And if we look at average river flow after warming and we make an average, it's more or less there are no big changes. On the other hand, there might have been changes at the local level. In fact, what climate models predict is an increase of rainfall at high in the north and south of the globe, and a decrease of rainfall in the tropical area, the Mediterranean, etc. So there is a lack of homogeneity in the changes, as I already mentioned. So, it's true that at the global level we didn't see many changes, but at the local level there might be changes. Also, some people say that if you look at the long time scale of rainfall, okay, you don't see any change. So yearly rainfall, no change. But some people say that with some physical reasoning, if you look at extreme rainfall, it has increased. And indeed, some data analysis show that not everywhere, but in some locations, it seems that extreme rainfall, with extreme I mean rainfall at the time step of hours and minutes, it seems that it has increased of about 7% according to the Clausius-Clapeyron equation, 7% per each degree of warming. And some scientists have recently found in Australia increases up to 18% of extreme rainfall. These numbers are important because if you listen from the media, there are some people saying that extreme rainfall has doubled, or I heard one meteorologist once saying 10 times higher, which means 1000%. It's extremely important to know that if you look at the data, as it's written here, we found increases in the order of magnitude of extreme rainfall, 7% per each degree, which means 7% from pre-industrial era, which means something that is barely effective on flood risk. Of course, there is an increase, but not as significant like 10 times. Okay. So this is for rainfall. What about river flows? About river flows, because river flows, I think they are mentioned here. Yeah, because here I am speaking about human influence on climate, and climate I mean temperature and rainfall, and then I dedicated a section to hydrology. Precipitation, we already discussed it, and this is long-term precipitation by month. It's a figure, it doesn't really deserve that we dedicate time now to it. And here there is a discourse on evapotranspiration. These are some graphs. I read reading them to you. Some graphs, it's an analysis of frequency and magnitude of daily rainfall over the globe. It's an analysis that I carried out with a colleague working in Canada. The paper was just accepted for publication a couple of days ago. And anyway, it shows what is the magnitude of increases in frequency and intensity of extreme rainfall. A similar analysis made over Italy didn't show any significant change, but this is daily rainfall. And some people say that the increase has been, is magnified when we look at shorter time scales. Okay, now let me talk about the river flow. River flow is later, let me see, because there is sea level. And just 1 second, because I want to make sure that I follow the same order. Yeah, this is river flow. Okay. Let's talk about after rainfall, now sea level. And the sea level is another variable that is extremely interesting for us, because sea level is affecting also water resources availability for saltwater intrusion. We will study saltwater intrusion next week. And as I said, sea level is relevant for us. It's relevant both in terms of extremes and average sea level. In terms of extremes, it's much relevant because if you have storms in coastal areas, these storms may indeed drive saltwater intrusion. Saltwater intrusion means that saltwater gets into the land and contaminates freshwater resources underground and the surface freshwater resources. Extreme sea level is governed mainly by winds, because storms are caused by winds. When we talk about average sea level, it's mainly governed by temperature, global temperature, or large-scale temperature. An increase of temperature at the global level causes ice melting into the mountains, but also from the Arctic, and therefore sea level rise. But also an increase in global temperature means an increase of volume of water in the oceans. If you increase the temperature, water expands, and this is one important driver of sea level rise. So sea level rise is not only due to ice